Thanks, Hong. So today we're going to be doing, sorry, some of the recording I didn't record. So we're going to do some Fourier examples, and it's really effectively how to do homework 13. So I have a sine wave. It's 155 peak to peak, and I'm going to run that. And then I'm going to look at the fast Fourier transform, and you can see that there's a peak. At effectively 50 hertz. All right. Now, these peaks and things are really just noise of the digital calculation, and it's in order to get it that noise floor so low, I set dot options num digit with such things to double precision, and options plot window size equals 0 is for no compression when it plots to the window. So that you're getting as accurate data as you can. All right. Now let's go to a linear scale. Zoom in. Well, we'll notice that we're almost, it says 106. Or wait, let's see if I can get it closer. So it's almost 110. All right. And the reason why it's not exactly 100, it rounds to 110, is because I didn't put in the exact value of the peak that I should have gotten to give me 110. Right, because the FFT naturally gives us the RMS value peaks, where in Scopy you can show the RMS or the amplitude. So if I want the actual amplitude, I just convert it, right? And now we're back to 155, all right? So that would be the amplitude. But it's a clear case of seeing that you can see that the FFT and LT spice does RMS. It's not exactly told to you in an easy way. But anyway, so we need to convert this signal into a DC. All right. And one way to do that mathematically is just take the absolute value of it. All right. But notice now that we've taken the absolute value, we should actually see that the frequency has doubled, although the RMS should stay the same. Okay. Now, yes, there's more noise, and that noise, well, actually, the absolute value does have higher harmonics, and so that energy is going into these higher harmonics. All right. So you can see 1, 2, 3, 4, 5, 6, almost 7. And so that energy gets pushed out, but also there's a DC offset where that energy went as well, but LT Spice doesn't show you the DC offset. Okay. So now I need to convert that to DC. I don't want, so now I'm on full wave. The 100 hertz is what I don't want, everything above. So I want a low pass filter. So I would just draw some kind of filter response like a low pass because I'm trying to get rid of these. Again, I'm trying to capture the DC part, but it just doesn't show up on an LT Spice. Well, if I use a low pass filter, okay, it takes time for it to reach its value, but there we are. We're getting what would be a DC, but with a ripple, or even you could think of it as a, well, in this case, it's 100 hertz hum. All right, and it just takes some time to get there. So it's what? Coming in at about 90 volts. So I just need to delete some things. So now I have about 90 volts, and I want to get around 2 volts, and this is a voltage linear dropout regulator. And so it should be able to, based on these two resistors, convert it into DC. But what happens when we run it, it starts getting really slow, all right? And acting what you might say very peculiarly. And that is because the maximum voltage for this device is 7 volts, and we're putting 90. And so Spice is just having a hard time with that. Okay. Oops. Let's just do undo. Okay. So that doesn't work quite so well. And so what we need to do is have a transformer. All right. And you can just look this up. This is, I'll just easier to show you. All right. But if you, the Analog Devices has a pretty good tutorial on doing that. All right. So I'm just going to delete. So now we can see that instead of going to 110, all right, we got a V peak of 155. We got a V peak of 112. Actually, it won't do derived things, but that's okay. So now this signal we could actually put into this filter, but it doesn't quite. There's issues with that in that if you attach anything to it, it changes the time constant and thus changes practically everything. So what we have here is a full wave rectifier. Let me move some things around so it's easier to see. which you may or may not have seen in your circuits class. Right. And it takes a differential signal, V plus, V minus, and it allows a sine wave to go through one way, allows a sine wave to go through the other way. And so you're always getting a positive voltage. Okay. So now it took that 12 volt amplitude sine wave, right, and then turned it into something very close to absolute value of a sine wave. So it adds waves. Yeah, Nick, it does. It adds the positive cycle. Well, I mean, really, it's taking the absolute value, but it adds the positive cycle and then subtracts the negative cycle so that it's an addition. Okay. So now we've got a signal that is in the right range, right? And it needs to be filtered. So here we have a filter, okay? Just a simple low pass filter. And you can kind of see that it starts off at 0 and then eventually gets where it's going. And so it's around 7.86. And then you can see a ripple with that. Yeah, Michael, that's right. And it also does it right. The half wave rectifier, it's simpler, and it's also used though in demodulation. But yeah, it's simpler, but that's about all that it has going for it. So now this is DC with a ripple, but if I were to add a load resistance like 500, right, it would change the total time constant, and then there'd be this voltage division going on, and it would make it quite difficult to get a steady output voltage for any load. So now we're a bit above 7 volts, and this is an LDO. This sets these two values set of what we want, and when we look at it, okay. Now, I'm sure it's rippling a little. It's just really hard to see, right? But now we've got a DC output, all right? What we could do, right, is look at all of these. Sorry. So there is still something going on at 100 hertz, right? But we're getting a DC value, which is being attenuated, and which isn't displayed, but that's kind of what's going on here. Oh, thank you. All right, so again, we're going for DC, and what we're seeing is less and less ripple. All right, and so you can see here's this very tiny thing that we're just about making out, but that kind of straight line is kind of indicating almost that you've got a DC source or you've got an integrator. All right. Now, That's great. I've converted it to DC, and now I can run op-amp circuits, right? But part of the problem that we needed to do is we needed to be able to drive the clock, right? And so microcontrollers have a clock, and these type of circuits which exist can take the 60 hertz or 50 hertz and actually use it to drive a clock. And if you might think I'd be able to use node 1 here, right? Because the 100 hertz is still there, right? And if we look at the, okay, we can see that the 100 hertz, the higher harmonics is there. We could still grab it, but it's got this DC offset that you can see that would make it harder to capture. Now, sure, we could try to subtract something, but if I have another side of the transformer, we call it conveniently clock, right? Well, now I got a sine wave, right? And if I and so now if I just pass that sine wave into a buffer, here's output here, 2.7 volts to ground, right? I'm basically have a sine wave that's too big, and so it'll stay zero when it's less than zero and stay the power supply voltage when it's greater than the power supply voltage. And so here we go. Here's our square wave that can be used as a clock signal. All right. And of course, you can look at that. And you can see 50. Now it's not perfect because notice there was a startup, right? So that's affecting it. But you can see that it's a square wave. Now, you know, really mathematically, you can do things. The circuits were a bit of a bonus, right? But how to take a 60 hertz and turn it into something, all right? How to convert the 60 hertz into a square wave, all right? We've done that. And then how do we get rid of 60 hertz that we don't want, right? That you have to figure out. Now, the next thing I want to talk about is we've been using Butterworth. Actually, I want to. This is actually something I was working on today. All right. And what this is a neural model. And I can model, you can take differential equations and put them into integral equations, which we've done for filters, right? The filter is really just, you know, an integral equation, but I've got x squared in the feedback loop, so it's nonlinear. So you can't do Bode plots with this, all right? But this is just a differential equation simulator, but you put it into an integration. Now, this is great, and you can turn this into op amps. That's 122. However, there's something called field programmable analog arrays, where rather than use op amps, this symbol is just a resettable integrator. all the integrators we've done so far, we don't reset them. And we have a multiplier, and we have this summer with a low pass filter. All right. And I can reconfigure this on a chip without having to do anything connecting wires. I can change gains, or I can change these all and then recompile it. So it's, if you're taking 118, it's just like using the field programmable array for digital circuits, but for analog. And it wasn't working. And I had a suspicion that it was the multiplier. All right. And it seemed that the multiplier didn't work for signals greater than 10 kilohertz. All right. All right. So I was trying to make sure that my signal did not go over 10 kilohertz. So this actually does have a solution, even though it's nonlinear, and it's an arctangent function. All right. So how do I make sure that this signal isn't going over 10 kilohertz? Well, the smallest frequency will be the period, right? And yes, it's going from -1 to 1. And so maybe there's no DC offset, right? If it's even the way I have it. But the smallest frequency will be 1 over that period, right? But all I have to do is look at the FFT. And it'll be easier to see it in linear. All right. And so there we are. That's about a kilohertz. And then you can see these higher order harmonics. We could get a little bit better resolution. But not much better. Okay, so now I know that if the fundamental frequency is below a kilohertz, and I have 1, 2, 3. Yeah, I mean, I have a harmonic at 10. There is data up here, but it has been reduced so much that it was able to figure out what to do. Now, something you might not know is that a way to test a multiplier is to actually have it square a sine wave, right? And then look at the FFT, right? And a squared sine wave does have a pure signal at twice the frequency. And if you're seeing things beyond twice the frequency, well, those are nonlinearities. I just pointed out because that kind of question was on an exam recently. Okay, so even for this totally nonlinear system, I was able to use what we learned in 110 to make sure to keep a certain frequency below what that multiplier could handle. Okay.
Professor,
Yes.
for the final, is any of this stuff going to do, or is it going to be like us seeing the graph and from there determine what the input or output is?
I would suggest looking at the old finals to see what kind of questions I ask. But, you know, here's a situation, apply the Fourier expansion and tell me what's going on and how to take a signal, how to keep a signal, how to get rid of a signal, how to filter it, things like that. Okay. Because right now, yeah, today's an application day. And so on the exam, I show applications and then you have to interpret it. Okay. But you wouldn't, that being said, you don't have to know any, this is for homework, right? Which is good to know because EEs do a lot of power supplies, tells you how it fits in. But knowing this circuit on the, knowing transformers, full bridge rectifiers, and this on a exam, no, right? Being able to interpret the absolute value of a sine wave, yep, you could see that, or a sine wave squared, you could see that, but more mathematical. I show this because I get this question a lot, okay? I'm trying to show you every place that it, like, I guess what I'm saying is this is my research project and I have seniors working on this, right? But it wasn't quite working. So even though this is advanced research, I used 110 to figure out the problem. Okay. But you know, designing a circuit to do all that, no. Or I could ask one take-home question and that would be it, right? So we've talked about the Butterworth filters, all right? And there's an algorithm to these constants, all right? And really, the Wikipedia page is great, right? They even show you these Butterworth filters with totally passive components. Now, sure, I would put an op amp with a buffer on the output here because you connect anything to this, right? And it's going to throw everything off, right? But they've got the constants, right, already broken up into first and second order equations so that you could use RLC or multiple feedback or Salin and Key building blocks, right? They've already kind of done the work, all right? But where is this algorithm coming from? Now it's in the book, okay? But the algorithm really is, the radius here is omega naught, right? And then you just keep these poles, right? However many poles they are, you split them up on the unit circle and keep them that distance apart from each other. So this circuit has 4 poles or 2 sets of complex poles, right? So that's 4. And so if I take 180 degrees and divide it by 4, right, everything should be, these poles should be 45 apart, all right? So here, and if it was an odd number, you'd have the pole here and then split and the rest along that, all right? So, and again, this is just the poles. Remember, it's the, so that is these poles are making the denominator, right? But it's the numerator that tells you what that filter is going to do, all right? So what I wanted, so so these numbers here, right? That's one pole. So you'd have one here, okay? This has 2 poles, right? You'd have one here and one here, right? And then 3 would have one here, one here, and one here. Then 4 is what you see, and then 5 all the way on up. They have 10. I'm not quite sure how practical that is, but I imagine 10 could be needed. All right. So that's the algorithm. Now for homework, I want you to come up with your own algorithm. All right. Now let me just try to be clear. This is my algorithm, right? I'm not claiming any claim to fame, but I want you to come up with an algorithm, all right, on your own. And the question is basically showing you how I did everything, right? So basically, I have a poll here, and then I come over, I just divide up the distance by whatever number of poles there are, right? And I just have a straight line back instead of a semicircle, right? Your algorithm could be, you know, a hemisphere or an ellipse, or maybe a backwards ellipse, or maybe a box, right? Just some kind of shape that you can turn into an algorithm. Now, in order to do this, though, you have to have the poles with the real and the imaginary. You can see I have 3/4 rather than in the, you're used to seeing this all multiplied out. You're used to seeing this all multiplied out. All right. But you can put it all into LT Spice, where here's my poles, right? You can download the file. And then, yeah, here's a transient response of that. Now, of course, I would only do the low pass, because low pass from the Laplace works fairly well, right? But here is the Bodie plot, which will be pretty accurate, all right? So you come up with your own thing, right? And then just do your best. It's a really open-ended question. You should have fun. But here's the thing, right? You know, one day we might be talking about the de Guzman filter, or the Stanfield filter, or the Coleman filter, or the Weiss filter. Okay? Could be you. So just come up with an algorithm. You don't have to do 7 polls like I did, but take it all the way through. Okay? All right. Just don't, I mean, I can tell if you draw this, right? Well, then I know it's the sample algorithm, right? I just want you to do your own, all right? And I'll leave it at that, okay? So that's the applications for today. What I wanted you to do is I'm going to break you guys up. I'm just trying to delete. There's, is that it's time to start reviewing. And I have some review assignments, and it's module 26, 27, 28 in-class activity. We did miss 26 because I was trying to get you ready for the homework. So even though today is 27, you come in, excuse me, launch it, and you'll see a filter, right? And you put in the gain. As the frequency nears 0, as the frequency nears infinity, then you come up with a transfer function, what the order is, 1, 2, 3, 4, 5, and then is it notch this or that, and then submit. Now, yeah, everybody, this is one of those random type questions. And so everyone will have slightly different plots, but you'll be able to help each other out. All right, so I'm going to break you guys up into 16 groups. Breakout sessions like we did way long time ago. Okay. Create. Okay. Assign it. I'm going to assign it automatically. If you are getting 26, then move on to 27. But that should be pretty good. So I'm going to open the rooms and you go and you join right away. Oh, got a question. I mean, it's good to do it now, right? But you can, I've opened those up to where you can keep doing them until the end of the semester. Okay. But really, this is our time to be with friends, to be with ourselves, and to concentrate on 110. So please don't take off. But no, it's not due like you have to hand it in at the end of class, right? All right, I'm opening the rooms. So the thing is if I look at this feedback network, and really these are two resistors, right? I really just have R1 and R2. Now, if I is 0, because we're saying that part of the op amp ideality is true, right? And this is V out, right? Well, then we could call that Vx, or the feedback part is just the voltage division. All right. Which is the beta. So if I make my summer, and in the problem for today, or the in-class thing, it was just AV divided by S. So then for the signal flow graph, we come in on the negative side, right? But rather than a function G of S, there is no S dependence. It's actually equal to beta, which is actually equal to that voltage division. All right. So the op amp is really a summer with a transfer function on the inside. The feedback network in this case is beta divided by S, beta. All right, so Q of S So in this problem, if this is much bigger than that, then AV will look infinite compared to it, right? Well, you can just write that as a shorthand, is the magnitude of that is much, much less than this. All right. Which really in this case is omega. And it's easy to directly find the frequency in question. That's what the midterm was, except it was this was the transfer function. Okay?
Yeah, thank you, Herb.
Okay. Anybody else have any questions?